Here's a solid mechanics problem that first-year engineering students might come across, and those are students who are doing either things like aerospace or mechanical or civil engineering. And if you'd like to see anything similar to this on the channel, or if you have any suggestions for any topics or specific problems that you'd like to see, let me know in the comments. So let's try to read the question and see what we have to do. We have a beam, and we are asked to find the normal force, shear force, and the bending moment at point C. Okay, which point C seems like it's in the middle of the beam. So the first thing I recommend doing is to draw the free body diagram of the entire beam, and then draw the reaction forces that are acting on it. Okay, so first of all, we have a support at A, and that's a roller support, which means that we only have a vertical reaction force here. So this is, let's call this RYA. And then at B, which is 1.5 meters away from the right hand side of the beam, normally we have two reaction forces. So we have RYB, and we also have an RXB, okay? Because this is a simple support, so simple supports have two reaction forces, a vertical and a horizontal one. And those are all the reactions that we have. So now I'm going to draw the external forces and moments. So what we have is that at the left side of the beam we have a moment, an external moment of 30 kilonewton meters. And then on this side, we have a point load, which is 10 kilonewtons in magnitude. Okay, and what we have to now do is to find the reaction forces. Now, before we do that, I will draw some distances. So this is 1.5 meters, this is also 1.5 meters, and here in between we have 3 meters. Okay, so let's first look at the equilibrium of forces in the x direction. So we have that all the forces acting in the x direction, or the sum of forces acting in the x direction, has to be equal to 0 for equilibrium to take place. And if you look carefully, we just have one force in the x direction, which is Rxb. So this means Rxb equals 0. Okay, so there's no other horizontal force that this reaction can balance, which means this reaction force is 0. And the next thing I'll do is I'll say the sum of forces in the y direction is 0. Okay, and usually you have to pick a sign convention. And what I usually recommend is all the forces acting upwards are positive, all the forces acting downwards are negative. So when I add up all those forces, I will keep track of their direction. So let's see what we have. We have RYA, which is positive. So we have RYA, and then we have plus RYB. Okay, and then we have minus 10, and the whole thing equals 0. Okay, those are all the forces, all the external forces that we have. So we have two reactions, and we have a 10 kilonewton force that's acting downwards, and that's where the minus sign is coming from. So this gives us that RYA plus RYB equals 10. Okay. So that's one equation, but we need something more to be able to find the reaction forces. And to do that, we are going to take moments about a certain point. And you can take moments about any point, but I will take moments about this point that I'll call P. Actually, this is point A according to the diagram, so let's call it A. So I'll say that the sum of moments about point A is equal to 0, okay? And as usual, we need a sign convention here as well. Okay, so with moments, I consider all my counterclockwise moments as positive and all my clockwise moments as negative. So about point A, this reaction force doesn't produce any moment. So here's what we have. we have this 30 kilonewton meter moment that we have to include as well, right? And that is counterclockwise. So that's going to be plus 30. And then we have the moment due to this RYB, which is also counterclockwise. So that is plus RYB multiplied by the moment arm, which is 3, like that. And then we have this force, which is acting downwards, and that produces a clockwise moment about A. Okay, so that's going to be minus 10 times, and the distance from A to this force is 4.5 meters. So we have times 4.5 equals 0. Okay, so 3 times RYB is equal to 45 minus 30 if we rearrange this, which gives us 15. Now keep in mind this is kilonewton meters at this point if you want to add units. So RYB, if you divide by 3 meters, you should get 5 kilonewtons, which is a nice round number. Okay, which also tells us that the reaction at A is 10 minus 5, so that's 5 kilonewtons as well. Okay, so we found the reaction forces. We now have to answer the question, which is what is the normal force, shear force, and bending moment in the middle of the beam, which is labeled as point C. Okay, and to do that, we are going to take a free body diagram of the first half of the beam. So this is what we have. We have half of the beam, so this should have a length of 3 meters. And then on the left-hand side, we have a moment of 30 kilonewton meters. Okay, and for the rest of the free body diagram, we have to express the effect of the right-hand side of the beam on the left-hand side of the beam. Okay, so in general, we have a normal force here. We have a shear force, which I'm going to draw according to convention as acting downwards. And then we also have a bending moment here, M, and there's also the reaction force at A, which is like this. Okay, so this is RA, which is in the middle of this 3-meter section of the beam. So this distance is 1.5 meters, and this distance is also 1.5 meters. Okay, so let's try to find each of those internal forces individually. So first of all, we'll start with the horizontal forces. This is the easiest part. So this tells us that N is equal to 0. Okay. Then we have the vertical force equilibrium. So the sum of forces in the y direction is 0, which means that RA, which is acting upwards, minus S equals 0. So S is equal to RA, which is 5 kilonewtons. So we found the internal shear force. So now all we have to do is find this bending moment. And to do that, we are going to take moments about this point C. Okay? Just to cancel out the shear force in the equation. So we have that the sum of moments about C is 0, meaning that we have M, which is this bending moment, which is counterclockwise, so we put a plus sign in front of it. And then we have this moment, which is also counterclockwise, so this is plus 30. And the only other force which is producing a moment is RA, so this is producing a clockwise moment. So we have minus RA, but we know RA is 5. And then times the moment arm, which is 1.5, equals 0. Okay, so the moment is going to be 5 times 1.5 minus 30, which turns out to be, let's see, minus 30, so that's minus 22.5, and those are kilonewton meters. Okay, so we have a negative value for the moment, so let's talk about that for a bit. I'm going to compile all the results on this page. So we ended up with N of 0, which is what we expected to begin with. We have a shear force of 5 kilonewtons, okay, and the fact that we have a positive sign in front of it means that our initial assumption that the shear force is acting downwards was correct. So this shear force is actually acting downwards. And we have a bending moment which has a value of minus 22.5 kilonewton meters, okay? And the fact that we have a negative value for the bending moment means that our initial assumption that the bending moment was counterclockwise was not correct, okay? So this simply tells us that the actual bending moment within the beam is clockwise. So you can either say that this is a counterclockwise bending moment of minus 22.5 kilonewton meters, or you can consider it as positive 22.5 kilonewton meters, but it's acting clockwise. Okay, and either of those two options are correct. And those are the normal here, normal for shear force and the bending moment, and that's the end of the question.